All right, we are recording. It is 1 p.m. We are live. So everybody, welcome to Statics. Everybody had a good 3-day weekend. Hopefully you got a little bit of rest and relaxation in and are recharged and ready to get things fired up again. Okay, just a couple quick announcements. I've got the attendance grades up to date on Blackboard. And then, like I said, we're keeping on with the same schedule that we have been for our homework. So you all turned in homework 2.3 today. 2.2 was graded and the solution's been posted. And then after class, you'll see homework 2.4, and that'll be due Friday. So any questions before we get things kicked off? All right. Okay, so today's kind of a big day because it might seem kind of strange. We're in lecture 7 and we haven't actually started applying statics. We're actually going to start looking at static equilibrium. We're going to start off with static equilibrium in 2 dimensions, and you'll see how our IJK notation, or specifically our IJ notation in 2 dimensions, is really going to make applying static equilibrium really, really straightforward. But before we do that, I want to take a second and review a topic in algebra that's going to pop up actually going to start popping up today, and that's looking at systems of equations and particularly 2 by 2. If you saw on Microsoft Teams, I posted a comment. Hopefully everybody has their scientific calculator with them. So if you took Engineering 111 and you still have your Casio, that's going to be a perfect calculator for simultaneous solution. You'll use it quite a bit. The TI-30X Pro is also a good one as well. So it's a good idea to just have that handy because we're going to be using that actually today. So with that, let's go ahead and get right into it. I want to start off by doing my quick algebra review. So let's talk about systems of simultaneous equations. We're going to start off looking at 2 by 2 systems, and then here in the next couple lectures, probably starting next week, we're going to look at 3 by 3 systems. It won't get any bigger than that for our course, so your scientific calculator will be able to handle it no problem. But let's start at this from just a basic algebra perspective. So it's probably been a while since you looked at problems like this. So let's take a look here at the slide. And I have here a system of equations. So I have 2 equations and I have 2 unknowns. So we have x plus 2y equals 3, and we have 2x plus 3y equals 4. And so you probably dealt with problems like this maybe in high school, or maybe if you took Math 127. I know that we usually cover this in our ENGR 111 course. But the idea is to find the values of x and y that satisfy both of those equations. So there's a magic value for x and a magic value for y that handles both. Let me see. I got a comment in the chat that said you lost sound. Did everybody else lose sound, or is it just Chad? You might want to. You might need to log out and then log in. You might try that. And if you miss anything, you're keep in mind we're recording. But yeah, try and log out and then log back in. I've had that happen in a couple Collaborate sessions, and that seems to do the trick. You also might need to close your browser and open it. So, but I'll check in here in a couple minutes, make sure he got in. Okay. All right. So back to our simultaneous equation. So the idea is to find these 2 magic values of x and y that satisfy both equations. So there's a value of x and a value of y to where if you plug them into both equations, it'll satisfy both of them. Now there's 3 approaches that you can use. I mean, actually there's quite a few, but in terms of just making sure that we all remember this, from high school or from Math 127 or what have you. The 2 that you usually learn to do by hand are either substitution or elimination. But I also want to focus on using matrix algebra and specifically using your scientific calculator to do a lot of the grunt work for you. So let's first review substitution. And so the idea behind substitution is you take these 2 equations, and it doesn't really matter what order you work in, But let's say we look at the first equation. So we take the first equation and we isolate one of the variables. So we have x and y. So if you look here, let me use my little mouse pointer. Okay, so here's my system of equations here. And we'll take this first equation right here and we'll isolate one of them. So when I say isolate, I mean x equals something. So x equals 3 minus 2y. That's just me taking the 2y and moving it on over to the other side. I saw Chad joined us back. Is the audio coming through? While he's logging in, I'll keep on. Okay, good. Okay. So I've got this expression for x. X equals, a pile of junk, 3 minus 2y. What I'm going to do is I'm going to take that expression and I'm going to substitute it into the second equation. So I use the first equation to isolate a variable, and then I plug that into the second equation. And I do my algebra work, I plug and chug, and I get y equals 2. And once I get y equals 2, I can take that and plug it into really either equation and get x equals minus 1. And so here you go. Here's those magic values of x and y. X equals minus 1 and y equals minus 2. If you take those values and plug them into either equation, you'll find that it works. And that's your first method. The second method is elimination. This is probably the other method that you did by hand. And so the idea is to take one of the equations and multiply it by a scalar. So for instance, if I take the first equation and I multiply every term in that equation by minus 2, I'll get, so here's that first equation. If I multiply it by minus 2, I get minus 2x, and then 2y times negative 2, I get negative 4y, and then this times this, I get negative 6. The idea is if I do that, look what happens to the x's if I add everything up. The x's will end up canceling because I have a negative 2x and a positive 2x. So they cancel, and so I add up my y's, add up my constants, and I get the same thing, and then I can either repeat the process or substitute. It's probably been a while since you've done this, but I know just about everybody in here has done problems like this in the past. My main purpose for this little review is just to get everybody back into that frame of mind, and then I want to introduce make sure that everybody's familiar with the method that you really will use, which is the using your scientific calculator. Okay. All right. You can also use matrix algebra to solve the system. So what you would do is you would rewrite that system in matrix form. And so what I mean by that is you have this square matrix that consists of all of these coefficients here. So the x coefficient's 1, and then this y coefficient's 2. This x coefficient is 2. This y coefficient is 3. And so I have this square matrix here of my coefficients. I have this rectangular matrix, this column matrix here that contains just the coefficients here, the 3 and 4. Now the idea is that you can, if I have it written in this format, I can take the inverse of this matrix, multiply it by that to get my answer. Now that can be a bit time consuming to do by hand, especially when you've got really, really big systems, 3x3s or 4x4s. But the idea is that your calculator can do this all on its own as long as you're comfortable with splitting it up into this matrix format. I've got here on this slide, this coming slide, these are some screenshots from the Casio. So if you all have a Casio FX115, which is, well, as far as I know, that's what we still use in Engineering 111. So just about everybody in here, you should be able to do the same thing. If you've got your Casio with you, on the Casio, there should be a mode button. If you hit the mode button, you'll see this menu pop up. It'll say like computation, complex, statistics, whatnot. Option 5 is what you're after. That's the equation solving mode. So you press the mode button, press 5, and then it brings up some options. What you want is option 1. Option 1 is the 2x2 system. Okay. So question, I have a TI-84 from calculus. Is that okay? That's fine. What you probably are going to want to do though is just let me say this, if you're comfortable doing the matrix computations, that's completely fine. I have no problem with that. One thing you do want to be aware of, Carrie, is that The TI-84 is not going to be permitted on the FE exam. That's the licensing exam, or the first licensing exam that you take right around when you're a senior in the program. So at some point, you'll probably want to get a one of those approved calculators, and we can talk, and I'll give you a few options. I'm not really worried about that now. If you can do these computations on a TI-84, totally fine with me, but you probably want to break out the user's manual if you're not familiar. But if you're familiar, A-okay. For everybody else, if you've got the Casio, the mode 5 and then 1, otherwise just you probably, if you have like a TI-36X, it's pretty similar. If you got any questions though, you can either message me in Teams or give me a call, and we can work through that. For the Casio, though, what will happen is when you go into mode 5 and then option 1, you'll see this window pop up. And what you do is you fill this, this matrix up with what you see from the equation. So the 1, 2, the 2, and the 3, that comes from the coefficients from your variables. And then the 3 and 4, that comes from what you have over here. And once you enter in all those variables and you hit equals, it just sort of does the work for you. And so I'm completely fine with that. But the long story short is you'll want to become comfortable with that, because we're going to be doing those types of problems actually starting today, and we'll do them quite a bit for the next few lectures and even throughout the semester. Before I get into actual, the portion of lectures, anybody have any questions about this? I know it's probably been a while since you've done these problems, and that's okay. We'll have some practice here in a bit. All right. Well, let's check it out. Let's actually talk about static equilibrium. We haven't actually talked about statics in the past few lectures. It's kind of interesting. I mean, we spent our first week just going through a lot of the math and the fundamentals and the physics, and then we've spent the past few lectures just describing what vectors are, but we really haven't gotten into applying them for static situations. So let's talk about that. Now, up until now, what we've done is we've just learned about the different ways of describing vectors, and what we've sort of honed in on as one of the more convenient means of expressing vectors is this new IJ notation. So if I have a vector, I could express that as so much of a component in the x direction and so much of a component in the y direction, and my x components are associated with the I vector and the y components are associated with the j vector. And so now what I want to do is I want to express the concept of static equilibrium. And this pretty much comes from Newton's first law. Remember, Newton's first law states that an object that is at rest or in motion will remain at rest or at motion until acted upon by an outside force. So for instance, let's say I've got my coffee cup here. My coffee cup's got some coffee in it, so it has some weight, and that weight is a force, right? Well, if I take this coffee cup and I set it on the table, what's happening is the coffee cup isn't moving, it's just sitting there. Well, why is that? Well, the coffee cup has a weight, and that weight is acting downward, right? I mean, if I had the coffee cup like this and I'd let it go, it would just fall down and hit the floor. So that is a force acting downward. So if we were looking at this, in x and y direction, that would be maybe j would be the y direction, that'd be acting downward. Well, why isn't it moving? Well, the reason it isn't moving is because the table is responding with a force acting upward. I take this coffee cup, I set it down, the table now has to hold it up. Drop the coffee cup. But it's hot, I've got my feet here, I'll burn my feet. Maybe if it was water or something, maybe I wouldn't mind. All right. So this coffee cup right now is in what we call static equilibrium. There is a force acting downward, that's the weight of the coffee cup acting downward. The table is responding with a force acting upward, and they're canceling it out. The resultant force on this system is 0. And in a nutshell, what is a system? How do we describe a system that is in static equilibrium? The sum of the forces on that system are 0. That is statics in a nutshell. Okay, and right now, and for every problem that we've been dealing with for the past few lectures, we've been dealing with systems where all the forces all meet at a common point. And when all the forces all meet at a common point, that system is static when the sum of forces are 0. Later on, when the forces don't meet at a common point, we'll have to introduce a new concept, and that concept will be a moment. And we'll talk about that later. But for when forces don't meet at common points, not only do the sum of forces have to be 0, but the sum of moments has to be 0 as well. But that's a little bit down the line. Now, how to tie together what we talked about before and what we're talking about now? Well, remember when we have a system in static equilibrium, the sum of forces has to be 0. But remember this IJ notation. I can write the resultant as the sum of all the x components times I and the sum of all the y components times j. Well, if I'm looking at this from a systems of equations perspective, I now have two equations. I have the sum of forces in the x direction have to be 0, and the sum of forces in the y direction has to be 0. So what will happen is I'll have two equations and I'll have two unknowns. So we'll be applying principles of static equilibrium to solve these types of systems, and we'll end up with 2 by 2 equations. Now, before we get into a problem, this is just something I wanted to bring up. This isn't, I believe this isn't going to affect our example today, but it is going to affect, I think, your homework problem. Remember that you have to make sure, this is statics, and statics is the study of forces. You need to make sure that when you're dealing with objects and you're doing your analysis, that you're dealing in forces. So if an object, if you have an object and it's being described with its mass, remember you have to compute its weight by taking mass times gravity, okay? And so in SI units, we express gravity as 9.81 meters per second squared. That's the acceleration due to Earth's gravity. In US customary units, that's 32.2 feet per second squared. And so many of the problems that we're going to do will reference an object's mass instead of its weight. Just make sure you're watching for that. That's an easy thing to trip you up. You start doing the problem and you realize you have to compute the weight, and all the forces are off a bit. Okay. Any questions before we dig into our example for today? Okay. All right. So what we've got here is I want to start looking at static equilibrium of a particle. And again, when we say particle, we're just talking about a system where all the forces all meet at a common point. Okay. So I have this system. I've got two cables that are connected on the roof, and they're connected to this point C that's supporting a load. And so these two cables are holding up a load at point C that weighs 400 pounds. And so what I want to know is how much tension, how much force are those cables experiencing in order to keep that load at C up, in order to keep it in static equilibrium. Okay, and so in order to solve this problem, we're going to introduce a concept today, and we're going to be doing this for the rest of the semester. We're going to draw what's called a free body diagram. We've kind of been drawing free body diagrams throughout the semester. We just haven't quite come out and described it that way. Basically, a free body diagram is just an illustration of all of the forces that are all acting on a given body. So in other words, I'm taking this physical situation and I'm turning it into a model that just describes all the forces. Because if I'm applying principles of statics, that's really all I care about. I just want to make sure I understand the forces being applied on this system. So with that, let me go ahead and stop the share. Again, if anybody has any questions as we're going through this, don't forget you can throw them in the chat, or you can turn on your mic. Any way works with me. So let me stop the share. Let me share the screen. And let me take my keyboard off here so I can use my Surface. Okay, allow. I wish there was a quick button to do that, because you have to go through all these menus to make that happen. Okay, so here's the problem. And again, I'm doing this in the Microsoft Teams notebook, so everybody in the class has access to this. So here's our problem. So we've got our weight C here, and we've got all of this. Let me start off by, let me make my screen bigger. let's start off by introducing this concept of a free body diagram. Now, first thing I'm going to mention is I'm going to draw my free body diagram of point C, simply because all of the forces all intersect at point C. So that's going to be the easiest point to reference. Okay, so here's my point. We'll call this point C. All right. So let's look at point C and let's see what all of the forces that we have that intersect at this point. So I've got, first off, I've got this, right? I've got this force here. That's that 400 pounds. Maybe we'll call this W for the weight, and so we'll express that in our vector notation. And so imagine your point C. Your point C, and you've got this load going down. You know, that weight hopefully isn't moving. Like if I was standing under that, I wouldn't want that weight to fall. And so in order for that weight to not move, I'm going to have some forces acting upward, and that's where these cables come in, right? And so I've got these two cables, one that kind of goes like that, one that kind of goes like that. All right, and so we'll call this TBC, we'll call this TAC. I heard a little chime on my chat. Hold on. We'll be doing a fair amount of cable problems in here, and on Friday we're going to focus on a particular type of cable problems because we're going to be looking at pulleys. All right. Okay. Now, first off, let's put some angles on here. So, just use, your principles of trig. If this is 30 degrees, that makes that 30 degrees. And that makes this 50 degrees. So we'll draw that out like that. 30 degrees. Call that 50 degrees. There we go. Okay. And so that's our free body diagram, just that point C and then all of the forces that go through point C. All right. Now, the next thing that we're going to do is we're going to describe our vectors. So let's put description of vectors. And specifically what I'm going to do is I'm going to use IJ notation. Okay. So let me do this. All right. So we're referencing all of our angles from the x-axis. So that makes our description of our vectors pretty easy. Let's start off with vector AC. Now, first off, the angle is referenced with respect to the x-axis, so I can use the cosine for the x component and the sine for the j component. Now, the question is, what's the magnitude, right? Like, what's the magnitude of vector AC? Right now, I have no idea. Like, that's sort of the whole point of the problem, is to figure out that magnitude. So what I'm going to do for this vector is I'm going to say TAC cosine 50 degrees, and then I have a question about this, times I, plus TAC times the sine of 50 degrees times J. Now, before I move on, does anybody, is everybody okay with this? Does anybody see a problem with the way I have my vectors written? I'll give you a hint. There is an error here. I want to see if anybody can catch it. Give you a hint. Has something to do with the signs. Pluses and minuses. No arrow? Well, no, it's not the arrow. I've got the arrow right here, and then this is just going to be the inside the parentheses is just a magnitude, so that can be a scalar. The TAC should be negative, the left direction. There you go. Exactly right. So this one's negative because it's going to the left. Now this one over here on the right, that one stays positive because it's going upwards, okay? But yeah, that's another thing that's kind of easy to forget are your positives and negatives. So usually I'll write the vector, write the magnitudes, and then I'll go back and say, okay, is that one supposed to be negative? That one's supposed to be positive. So that's easy to kind of accept. So I always like to try and take one look at that before I move on. That's yeah, good eye. I'm glad you caught that. Okay. Now, that's this vector. What about TBC? Well, TBC, again, I'm going to do the same thing. The angle is referenced with respect to the x-axis, so I can just use cosines and sines, just like I conventionally would. And so this is TBC times cosine of 30 degrees I plus TBC sine 30 degrees J. Make sure, did I miss a question, Chad? Yeah, X is name. There you go. Okay. So far, so good? All right. Now, there's still another vector. There's one I forgot, and that's the weight. Like, there's still the weight acting, the 400 pounds. I can't forget that. That's the whole point of the problem. All right. Now, here's my vector. I've got a component times I, and then a component times J. What's the component times I? Just want to make sure everybody's paying attention. Like, what do I put in here? Exactly right, 0. There is nothing here. Now, what about J? What goes in here? Now, okay, so it's not 400. There you go. It's negative 400. There you go, because it's going downwards. So negative 400, and we'll say pounds. Remember, that's my shorthand for the pound symbol. Okay. All right. Yeah. So just make sure. Yeah, that's easy to trip up a bit. Okay. All right. So up until now, this should be stuff that you're familiar with. We've done this in previous problems, taken vectors and expressed them in this IJ notation. Now here comes the new stuff, okay? Now let's look at equations of static equilibrium. Okay, I'm going to scroll down a bit, give myself a little bit more room to write so I'm not squunching it there on the bottom. There we go. Okay. So remember, up until now, we've got two equations of static equilibrium that we can apply. We've got the sum of forces in the x direction equals 0 and the sum of forces in the y direction equals 0. Okay, so these are the new ones. So let's apply each of the equations one by one. Now, like I said earlier, this IJ notation is really going to make our this part really, really easy. And here's why. Okay, let's look at these three vectors. I've got the tension in rope AC, the tension in rope BC, and then the weight, each of those three vectors. And I've got a pile of junk times I plus a pile of junk times J. Well, let's go back to what each of those mean. Remember, what's the pile of junk times I? That's the magnitude of the force in the x direction. And then the pile of junk times J, that's the magnitude of the force in the y direction. And we've already got our signs, the positives and negatives. We already got that part figured out. And so the really cool part is all I have to do for the sum of forces in the x direction is I just add up all the stuff that's next to the i's. And for the sum of forces in the y direction, I just add up all the stuff that's next to the j's. So what I can do is I can say negative TAC cosine 50 degrees plus TBC cosine 30 degrees is 0. And so all I'm doing is just adding up all this and saying it has to equal 0, because that's what the sum of forces in the x direction means. I mean, these are all the forces that are acting in the x direction. So the sum of those forces has to be 0 for the object to stay motionless, for it to stay sit still. Same thing with the y direction. I just add up all of those. So TAC sine 50 degrees plus TBC sine 30 degrees minus 400 pounds equals 0. That's simple. And that's basically all we have. All right. Now, what I'm going to do is I'm going to rewrite these equations just a little bit, and you'll see why here in a second. So I have TAC negative cosine 50 degrees. So in other words, I'm going to have the variable and then all the stuff multiplied by it. TBC cosine 30 degrees is 0. And so I'm going to sort of box this and say that this is equation 1. And then I'm going to kind of do the same thing here on the second one, but I'm going to take that 400 pounds and I'm going to move it on over to the other side of the equation. So I got TAC, sorry, hold on. I can do that a little better. Sine 50 degrees plus TBC sine 30 degrees equals 400 pounds. Okay. There we go. All right. So before we move on to like breaking out our scientific calculators and seeing if we can chug all this out, does anybody have any questions about how we got to this point? Because I want to make sure that the next part is clear. I don't want to like jump forward too fast into the next step. I'm going to write this part down here. All right. Okay, so let's look at these equations. I've got TAC times negative cosine 50 degrees. And I'm going to rewrite them just to make sure that we're clear on what happens next. Okay, so here's the equations written in just, equation form. Now what I'm going to do is I'm going to take these equations and I'm going to rewrite them, but I'm going to rewrite them in this matrix format. And the reason I'm going to do that is because that's going to make it a lot easier for you to enter those values in the calculator. And so the way that I do that is I just take each of the coefficients next to those variables and start filling in my matrix. And so that's why this first equation, I have TAC just times a pile of junk. And so that pile of junk is negative cosine 50 degrees. And then cosine 30 degrees. And this one is sine 50 degrees. This one is sine 30 degrees. And sometimes you might find, like, sometimes when I do this, sometimes I'll put myself like a little tiny dashed line here, just so I know what terms are where, and so I know where the positives and negatives go. And this is TAC, TBC equals, and then this is 0, 40. Okay. All right. Let me see if I can move that over a bit so it's not too squunched up there. Oh, hold on. Oh, Oh, I messed it up. There we go. That's a little better. Okay. Now, what I'm going to do now is I'm going to show you how you would solve this on your Casio. And if anybody has a different calculator, you'll probably need to either, like I said, break out the user's manual or maybe find like some YouTube tutorials or something like that. But keep in mind, if anybody has any questions, you can call me during my hours and we'll work through it together and figure it out. We'll break out, a Teams chat and whatnot and do what we need to do. Okay, so, oh, I forgot to turn my pen back on. All right, so Casio FX. All right, hold on. I heard a alpha zoom to get the matrix. Good deal. Thank you. Maybe I'll try and compile like a list of, because I'm sure it's YouTube. I'm sure there's plenty of people who've done it for various calculators. Maybe we'll try and compile that or something. All right. So you're going to go to mode. And then it's option 5 and then option 1. And what you should have is a table, and what you're going to enter in that table is the following. You're going to enter negative cosine 50, you're going to enter cosine 30, and then your 0, and then sine 50, sine 30, and then 400. So this probably goes without saying, but make sure that when you're doing this, that your calculator's in degree mode. Unless you want to try and convert those angles to radians, you can go ahead and do that. And so when you do that, you press enter on each one. When you press enter again, it should give you an X value and a Y value. So I'm going to give everybody a second, and I want to see if you all are getting the X and Y values that I got. So take a second, go through your Casio, and see what you get. Oh, somebody was right on it. Uh-oh, we've got answers and they've been seconded. That's what I like to see. So when you do this in your calculator, you should get X equals 351.75 pounds and then 261.08 pounds. And we got a lot of people got that. That's what I like to see. Is there anybody that's having a problem getting that? One thing I'll say, if you are having a problem, make sure that you check the signs, not the cosines and sines, but that first value needs to be negative. So it's the negative cosine 50, and then everything else is positive. Excuse me. Oh. That's funny. All right. Now, what does this mean for our answer? Well, it's what the Casio is spitting out is X equals some value and Y equals some value. And the way that we wrote this, the way that we organized our equations, the first row was for TAC and the second row was for TBC. So therefore, the tension in row AC is 351.75 pounds. Maybe I'll write the letters just to be different. And this is BC is 261.08 pounds. And that's my answer. I'll erase them there because this was just the number of results from the calculator. And that's it. So those are the independent values of the tension in the rope required to keep those ropes in equilibrium. And one of the things that you could always do to check to make sure those values are correct is to go back here to this equation 1 and this equation 2 and see where I have a TAC and a TBC. Well, plug in 351.75 and 261.08. Make this value that and that value that, and see if you actually get 0. In equation 2, plug in that value there and plug in that value there and see if you get 400. Now, if you're just typing the values out, you might not get 400. You might get, I don't know, 399.92 or what have you. But, you know, just rounding, that's close enough for government work. Any questions? All right. Now, what we're going to do next time, I want to pull something up since I've got my screen share. I'll go ahead and sort of briefly introduce my topic next time. Oh, warning. Next time, what we're going to do is we're going to continue this example, this problem looking at static equilibrium. I've got an example that we're going to do tomorrow or on Friday that's a bit more complicated. There's a bit more ropes, a bit more stuff going on. And then what we're going to do is we're going to look at a particular type of statics problem involving pulleys. Pulleys are they're a very common sort of riddle, if you will, in statics. You know, looking at the tension in the rope or the cable in a given pulley. And so we're going to look at my PDF isn't liking me right now. I'll look at that later. But we have a couple examples where we're going to look at exploring the use of exploring pulleys and how that works in various static situations. I want to pull something up with your homework real quick. So let's see. This is your homework assignment. It's just going to be textbook problem 247 and 249. Let me see if I can pull up the images because I kind of wanted to mention something real quick before we call it. Oh my. I don't want to pull up my solution. I just want to pull up the problem. Okay, so this is problem 247, and this is problem, let me skip ahead a bit. This is problem 249. So if you can handle the problem that we did in class today, you should be able to handle these. There's only two things I'll point out. One, just make sure that you're careful with your input values. You know, just make sure you look at the problem, make sure you're dealing in forces. But the other thing is just make sure that you're being kind of careful with the angles. Some of the angles in these problems are measured from the horizontal, and some of them are measured from the vertical. So just make sure that you're using the right trig functions when you split it up into x and y components. But other than that, if you can handle what we did today, you should be able to handle what we've done, what you'll have for your homework assignment. That'll be due Friday at 1, and then we'll get into pulley exercises. Next week, we'll start to explore some 3D before we move on to the next chapter. Any questions before I go ahead call it for today? We might be ending a little bit early. Prop the screen up a bit. Well, all right. I'm going to go ahead and end it early, but one thing I will mention, again, if you're using a calculator that's not the Casio and you have any questions on how to do that simultaneous solution, we can probably work it out. Again, my office hours are right after this from 2 to 4, and I've got office hours tomorrow as well from 10 to noon. But I'm pretty easy to get along with. If you need to find me, just let me know. I'm going to go ahead and stop the recording. And with that, I guess we'll end.